In this video, we are going to do two examples of using MacLaurin series to estimate values. This is going to use the MacLaurin series for e to the x. In the first example, we will estimate the value of e, and then in the second example, we'll estimate the value of the fifth root of e. So both of these quantities do sound kind of intimidating to estimate, but we're going to find that MacLaurin series makes this not too terrible, actually. So the number e, you've probably seen it before. It's called Euler's number, and even though it has this spelling, it's not pronounced Euler, it's pronounced Euler. So like the Edmonton Oilers. I drew this graphic because whenever I see the Edmonton Oilers logo, I want to draw this, so I had to get it out of my system. But it also should help you remember to pronounce it Euler and not Euler. So anyway, e is not a rational number. The decimal expansion of it goes on infinitely, and it'll never fall into an indefinitely repeating pattern. So here I wrote out approximately the first 50 digits. This is really to help you kind of see that this isn't a very predictable number. We can't really tell what the next term will be. And because of this, it might make it seem like this could be a very difficult number to approximate. However, we have MacLaurin series, so we can actually use those to go ahead and do this. So the MacLaurin series for e to the x actually has a very clean representation. It's just the sum of from n equals 0 to infinity of x to the n over n factorial. And in this particular case, since the series converges everywhere, it means that the series actually equals the function. So we can use the MacLaurin series to estimate e to any exponent. But since the MacLaurin series is expanded about x equals 0 by definition, then the closer the exponent is to 0, the faster the series will converge to the actual value of the function. So in the first example, we're estimating e, which is e to the 1, so x equals 1 here. So we're not super close to 0. Mathematically speaking, you can get much closer. But we're definitely close enough that we can get a good estimate in a reasonable amount of time. So in order to do this estimate, we're going to use a finite sum. We can't do the infinite terms of the series and sum them all up by hand or even by punching it into a calculator. So we do a finite sum to estimate e. And the first time through, we're going to do the sum using the third degree MacLaurin polynomial. So this is the sum that corresponds to just summing the first 4 terms for when n equals 0, n equals 1, n equals 2, and n equals 3. So if we sum these terms, we get 1 over 0 factorial, which is just 1, and then 1 over 1 factorial, which again is just 1, 1 over 2 factorial, which evaluates to 1 over 2, and then 1 over 3 factorial, which evaluates to 1 over 6. And then if we add these up, we get 2.6 repeating. So as you can see, this gets us kind of close to the value of e, but we do want to do better than this if we're estimating e. Generally speaking, just getting something that rounds 2.7 usually isn't enough accuracy. So to get a better estimate, we're actually just going to sum a few more terms and see how that comes out. So I'm going to sum the first 11 terms instead. So this corresponds now to the 10th degree polynomial. And in this case, we get 1 plus 1 as we had before, plus 1 over 2 factorial, 1 over 3 factorial, plus, and so on all the way up through 1 over 10 factorial. And if we put this into a calculator and see what it evaluates to, we get 2.7182818, and then it goes on from there. I only wrote out these first 7. Yeah, sorry. I only wrote out these first 7 decimal digits after the 2 because these are the values that are the same as the actual value of e. So by summing up using the 10th MacLaurin polynomial, we already have e accurate to 7 decimal places. And you can imagine that if you're doing this on a computer, you could easily add more terms to the sum and get even closer to the value of e. So the method of using a MacLaurin series to estimate e shows us what actually happens behind the scenes when we're using a program such as Wolfram Alpha in order to do computations. It's not going to store e to indefinitely many decimal places, but it can produce e to any number of decimal places at any time just by using techniques such as this. So it doesn't necessarily use the MacLaurin series. There may be other techniques that converge faster. But the moral of the story is that if you are using a program like Wolfram Alpha, it is going to use techniques, maybe a finite sum of some sort, in order to estimate values. For the second example, as I mentioned earlier, we're going to use the MacLaurin series for e again, but this time to estimate the value of the fifth root of e. So the fifth root of e is the same as e to the 1/5 power, which is e to the 0.2, which in this case means that x is 0.2. And 0.2 is much closer to 0 than 1 is. And if you recall, the closer we are to 0, the faster the MacLaurin series is going to converge to the function value in general. So we're just going to do this example using a degree 2 polynomial. Partly because if we use a degree 2 polynomial, we can just do this by hand. And it's really fun to see that you can, well, depends on your definition of fun, but it's really fun to see that you can estimate something like the fifth root of e, which sounds really complicated, by doing a small calculation by hand. So fifth root of e is approximately the sum from n equals 0 to 2 of x to the n over n factorial. And then if we plug in x equals 0.2, we get 0.2 to the 0 over 0 factorial, so that evaluates to 1. Then we have 0.2 over 1 factorial, that evaluates to 0.2. And last, we get 0.2 squared over 2 factorial. So 0.2 squared is 0.04, and 2 factorial is 2. So this gives us 1 plus 0.2 plus 0.02. We get that last term just by dividing 0.04 by 2. And then we can add this up, and it's 1.22. So our estimate is 1.22. And if you calculate the actual value for the fifth root of e, it starts with 1.22 as well. So we're accurate for the first 2 decimal places. And in the decimal expansion, you'll see that the next number is a 1. So not only do we have 2 decimal places of accuracy, but it's even closer to this than if it were like, 1.22999 or something. So this actually gives us a pretty good estimate, and we were able to do this very quickly and by hand. So that is all for these examples. Thank you for watching, and continue to watch the other videos on MacLaurin Series.